Hi there, this is Anastasio G. Pandalian here and welcome to my YouTube channel. And in this video, we will be discussing about the regenerative cycle, the closed feed water heater. So there are two setups of this regenerative process, the closed feed water heater. We have first setup, have the components of a turbine. Here is the turbine, the steam generator, the condenser, the pump, the closed feed water heater, and the trap. So let's begin. First, we have here at point 1 with pressure 1 and T1. Okay. Now the steam expands at pressure 2, but a mass M2 has been extracted while the remaining mass continues to find work or to create work at point 3 with pressure 3. So the remaining mass here is 1 minus M2. Now, this is 4. Okay. It goes out from the condenser. It rejects heat. It goes inside in the pump. It increases the pressure at 5. However, in a closed feed water heater, the liquids that is coming out from the pump and the steam that is coming out from the blade point of your regenerative does not mix. Imagine yourself pouring some boiling water on a pipe with water inside. So the water in the pipe gets warm and hot. So it's the same analogy to that. Still, they do not mix, but there is a transfer of heat, and the pressure of the water inside the pump or the pipe does not change. Okay, so we have here at 6. We have here also the condensate coming from the drip condensate coming from the mass extracted at pressure 2 is at saturated liquid. So we label this at 7. And a trap. A trap has this purpose of reducing the pressure of the saturated liquid, but the process is isenthalpic, so constant in enthalpy. And those we have to remember that this is the constant enthalpy line. We'll draw here in advance. Okay, this is the constant enthalpy line. Okay, there are a lot of constant enthalpy lines like this, that. Okay, so for the sake of illustration, we'll just discuss this one. Okay. Hey, so we have the air goes to point 8. Hey, so what is really happening? First, given point 1, pressure 1, temperature 1, you can find your entropy 1 and H1 in your steam table. Now at point 2, where the mass has been extracted, point 2 has this assumption that S2 is equals to S1. Okay, if you draw that in the TS diagram, this is your point 1. It has a constant entropy, so this is your point 2. Okay, the same entropy. Okay, and here we illustrate that it produces work from turbine 1, 2. Okay, now how to determine if the S2 is at saturated liquid or at superheated liquid? Okay, it should be that Sg at pressure 2 must be greater than S2, which is equals to your S1, then it is at saturated. Otherwise, if Sg at pressure 2 is lesser than S2, then it is superheated. And you have to interpolate. Okay? So the process of interpolation, either thermodynamic, computer-aided thermodynamic tables, and the interpolation itself is attached here within this video. You can click in the description below. Okay. So if it is saturated, then you have to find the X, the quality X. So what is the quality X? S2, which is equals to S1, which is equals to SF at pressure 2. Okay, this 2 designates at pressure 2 plus X2 SFG at pressure 2. Then you'll find your X2. Okay, then you can find your H2 is just equals to HF at pressure 2 plus X2 multiplied by HFG2. Okay, so at point 3, where the remaining mass expands further at pressure 2, pressure 3. Okay. However, S3 is just equal to S2 is equal to S1, as we have illustrated here. Okay. It's just a straight line where L1 equal to S2 is equals to S3, since we did not assign any turbine efficiency to that, and it is doing work turbine 2, 3. Okay, this is your point 3. Okay. Now, once again, if you want to determine if it is at saturated or a superheated state, you have to look at these qualifications. Now, in this case, if we think it is saturated and we found it is saturated liquid, so we have S3 is equals to SF3 plus X3 SFG3. Those you may find your X3 in order to find your H3. Okay, which is equals to HF3 plus X3 HFG3. Okay, now at this point, the remaining mass 1 minus M2 gets inside the condenser and was condensed to to the point of, it becomes saturated liquid at point 4. So at point 4, let me draw a line so that to conserve space. Okay, at point 4, pressure 4 is just equal to pressure 3. As we see it, the process in the condenser involves isobaric process. However, your enthalpy H4 is equals to HF at pressure 4. Okay? Okay? So we want to find the value of your V. 4. So that we may use it in the pump, work of the pump. So this is V4 is equals to just VF at pressure 4, which is also equal to pressure 3, of course. Okay? Now the work of the pump becomes V4 times pressure 5. However, your pressure 5, okay, since there is no mixing involved in here and your pressure 5 must be equal to pressure 6, thus your pressure 5 is also equal to pressure 1 because it's just a line or a tube which is being poured by hot water, and the resulting effect or the effect of the pouring hot water in a tube, the water inside the tube becomes hot enough so that lesser heat, okay, is needed to produce pressure 1 and T1 at point 1. So P5 is just equal to pressure 6, which is also equal to pressure 1, okay, minus pressure 4, which is also equal to pressure 3. Okay. Now at point 5 is that H5 is just equal to work of the pump plus H4. Okay. At point 6, H6 is just equal to, okay, okay, this is your point 5 here, okay. If we illustrate that here, this is your point 5 here, this one. Okay, it was exaggerated, so don't get confused. We're applying work of the pump here, so it increases the pressure equal to 5 and equal to 6. Okay, the main effect of pouring the mass M2 is that the mass M2 exchanges heat with the feed water heater or the feed water that is coming out from the pump at point 5, and it exchanges heat, or the heat gets absorbed by the water, the feed water, and the steam itself condenses to a certain point where it becomes a saturated liquid at pressure 7, which is also equal to pressure 2. Okay? So H6 must be, must be HF at pressure 2. Why is that so? This is your point, say point 7. No, where is it? M2 is that this is your, okay, this is your 7. Okay, this is your 7 where the heat, the steam you extracted exchanges heat with the water that goes in, okay, from the coming from the one from the pump. So this is your point 7. The effect of that is the same. This one is your zero point 0.6 with the enthalpy because this is an isenthalpic process. Okay? H6 is just equal to H7, where H7 is just equal to HF at pressure 2. Okay? So 7 is equals to H7 is equals to HF at pressure 2. Okay? Hope you understand that. Therefore, the needed heat QA has been reduced. Instead of H1 minus H6, I mean H1 minus H5, it becomes H1 minus H6. Okay, there's a reduction of heat needed. Okay, look at that. Which is the greater distance is the the 1 and the 5 compared to the 1 and the 6. Okay, so in the trap, this is also an isenthalpic process where there is a reduction of pressure. Okay, the reduction of pressure. Okay, so if you reduce the pressure, the enthalpy is the same. However, at this point, your M2 is being mixed in the condenser. Okay, so hope you're clear with that. Wherein H8 is just equal to H7. Okay, and it is carrying the mass M2. Look at that, oh. M2. Here we have M2. Okay. In 7 and also in 8 we have M2. Okay. So the main problem now is how do you solve the mass M2? So let's draw the line here. Okay. How do you solve the mass M2? Mass M2 is simply you put, okay, here a free body diagram, energy in, energy out, energy in, energy out, M2, H2, M2, H7. Okay, you look at the mass. The mass in the, say, in the closed speed water heater goes out as the same M2, goes into the trap and goes out the same as M2. However, it is being rejoined here at the condenser, wherein 1 minus M2 plus M2 is just equal to 1. So we have here 1 and H5. Also within here is 1 H6. So what goes in goes out. Energy in equal to energy out. So therefore, energy in M2 H2 plus H5 is equals to, okay, when you multiply 1 by H5 is equals to H5. When you multiply 1 times H6, this is H6. So H6 plus M7 H7. Those, your M2 is equals to H6 minus H5 over H2 minus H7. Okay? So those we will compute the work now. So the work of the pump is the same, but the work of the turbine is now work of turbine 1, 2 is just equals to H1 minus H2. Okay, sorry. Let me erase that. H2, the work of the turbine 2, 3 is equal to 1 minus M2, which has already been found, times H2 minus H3. The work of the pump is the same. So we have the work net is equals to work turbine total. So we add work turbine 1, 2 and work turbine 2, 3 minus work pump. So therefore, the thermal efficiency is equal to work net over QA. Okay, so this is the first closed feed water heater setup. The next closed feed water setup is it involves the steel, the boiler, the turbine, the condenser, two pumps, closed feed water heater, and a certain junction wherein mass of liquid mixes. Those we will label that as say 1, pressure 1, T1. Okay, this is 2, pressure 2. Still we extracted steam, M2. However, the steam, instead of going back to the condenser, it is being forwarded, okay, to a junction with the use of the pump to equalize the pressure, okay, of point 1. So this one is 3, pressure 3, where the remaining mass is 1 minus M2, okay, and this is your point 4, 1 minus M2 still has been say doing that work. So this one is 5, still 1 minus M2. Okay. 6, still 1 minus M2. And at this junction, where we have the output of this 7 is now the unity, because M2, okay, goes inside the closed feed water heater. It is being at saturated liquid at 0.8, and it is being pumped to a certain pressure equalizing with 0.7, 0.6, and 0.1. So this is your 9. Okay? So how we do the analysis of that? This one is your 0.1. This is your pressure 1, pressure 2, pressure 3. Also, it expands, okay, producing work. Turbine 1, 2 to the point 2, where a mass M2 has been extracted. Okay, and further producing work to the point 3, where work turbine 2, 3 is produced, but the mass is now 1 minus M2. Okay, it goes into the pump at point 4, after rejecting heat QR. Okay, this is your point 4, where heat rejection involves 1 minus M2 times H3 minus H4. Okay, so this is your point 4. It is pumped to a pressure of 0.5, which is also equal to the pressure of 0.6, which is also equal to the pressure of 0.7. Okay, so goes the same with this one. Not to exaggerate, this is your 0.5. Okay, now the pump, there's a pump also application here. And we notice we go down to the condensate. This is your 0.8 here. Okay, the steam that is coming in the closed feed water heater has been condensed and still mass M2. Okay, of course this is mass M2. This is 1 minus M2. Here it goes inside in the pump and still 1 minus M2. It goes out in the closed feed water heater but still 1 minus M2. In the later part, wherein at the junction it is being joined with M2, so it becomes 1. So this is the effect of your uh, closed feed water heater here. So this is the effect of your closed feed water heater where H is constant. Okay, to avoid confusion, where H is constant. That HC. H8 is equal to H6. Okay, it goes in the water that is coming up from the pump, goes to uh, closed feed water heater and gained heat. So it becomes at 0.6 here at this point. On the other hand, the mass that is coming, that is from point 8 has been forwarded by a pump here. Okay, has been forwarded by the pump, which is equals to 9. Okay, therefore there is a certain mixture here wherein 1 minus M2 with enthalpy coming attached to it at 0.6 is being mixed with the M2 with enthalpy attached to it at 0.9. So at this in between, we call this as 7. Okay? So we may add work pump here, work pump 1. This is work pump 1. This is pump 2. 2. Okay? So it is in between the 7, the resulting enthalpy is in between 6 and 9. Okay? So there is a heat addition wherein QA now is equals to H1 minus H7. Okay? And there is also a work of the pump here, 2. Okay? So we want to determine the enthalpies of that. We want to solve. So there is the point 1, pressure 1. T1. We can solve H1 S1 at point 2, pressure 2, assumption of isentropic process S1 is equals to S2. We can find the either we have to weigh out if it is saturated or superheated. So if it is uh, SG is greater, no, SG at point 2 at pressure 2 is greater than S2, which is also equal to S1, then it is saturated. But if SG at pressure 2 is lesser than your S2, then it is superheated, which you have to interpolate. Now, interpolation, once again, are attached in this interpolation, and computer-aided uh, lectures are attached in this description below. Okay? Superheated region. So, in this case, if we find that SG at pressure 2 is greater than your S2, then we may have to find X2, wherein S2 is equals to SF at pressure 2 plus X2 SFG at pressure 2. Those you may find your X2, and then you may find your H2 is equals to HF2 plus X2 HFG2. Now at point 3, pressure 3, with the assumption of isentropic process, we have S3 is just equal to S3 is just equal to S2, which is also equal to S1. Then in this case, if it is saturated, we'll have to do the work like S3 is equals to HF at pressure 3 plus X3 SFG at pressure 3, where you may find your X3. Those, your H3 is equal to HF at pressure 3 plus X3 multiplied by HFG at pressure 3. Okay? So this is it. That. Now at point 4, okay, we'll deal with the mass later. Okay, let's find the enthalpy first. At point 4, pressure 4 is just equal to pressure 3. And your H4 is equals to HF at pressure 4, wherein equal to pressure 3. Now, since it goes into the pump, we will need to find the specific volume of V4, which is also equal to VF at pressure 4, which is also equal to pressure 3. Those your work of the pump, okay, at the initial calculations, work pump 1 is equal to V4 times pressure 5. But your pressure 5 is equal to pressure 6. Okay? Pressure 6 in the assumption of isobaric process, and pressure 6 is equal to pressure 7. And pressure 7 is just equal to pressure 1. Okay? Minus pressure 4, which is also equal to pressure 3. Those, you may find the enthalpy of your 5. Okay, 0.5, pressure 5. In the assumption, we have pressure 6 equal to pressure 7 equal to pressure 1. Okay? And pressure at this point, we have H5 is just equal to H4 plus work pump 1. Okay? We will deal later with the work, but now we are more concerned on the enthalpy. So we will first do not mind the 1 minus m2 mass. Okay? We have to find first the enthalpy. Now at point 6, okay, this is your, say, point 6 here, coming from point 8 with equal enthalpy. Those your enthalpy of point 8 and point 6 are equal, which is equals to HF at pressure 2. Okay? Point 6 is the same as pressure 6, 7, and 1. However, your enthalpy H6 is just equal to HF at pressure 2. This is the effect of your closed feed water hot heater regeneration. Okay? This is the effect once again. Now again, point 7 is not known since we have to determine the say the mixture result. So wherein the initial mixture establish the equation first, H6 and energy equation and mass equation of M2. However, M2 multiplied by H9, of course we don't know the H9 yet, and the resulting is H7. Okay, so our main concern is the H8 and H9. Okay, so therefore, I will provide space later to this one. Okay, like that. Okay, so therefore, your at point 8 with the same enthalpy at H of 6. So which is H8 is just equal to H6. It's just equal to HF at pressure 2. Now, again, we may need to find the specific volume because there is a pump involved in here. So we have the V8 is just equals to VF at pressure 8, which is also equal to pressure 2. Okay? Those we may find the work of the pump 2 equal to V8 multiplied by pressure 9, which is equal to pressure 7, which is also equal to pressure 1, minus pressure 8, which is also equal to pressure 2. Okay? So therefore, you establish the work of the pump here. And those, the 9 is equals to H9 equal to H8 plus work of the pump 2. Now, therefore, in this equation, we go back to the point 7. We will still establish the energy flow, which is mass in, mass out, energy in, energy out. So H7 is the out minus, okay, 1 minus M2 H1 plus M2 H9. Okay, there you may find your uh, equation here with the needed data coming out from the energy equation of your closed feed water heater. Okay, So this is 1 minus M2 H5. And still here on this one, 1 minus M2 H6 goes in, M2 H2 goes out, M2 H8. Okay, energy in, energy out. Throw some arrow to that. So energy out, energy in, M2 H2 plus 1 minus M2 H5 is equal to 1 minus M2 H6 plus M2 H8. Okay? And those becomes M2 M2 H2 minus H5 minus M2 H8 minus H6, which is equals to H6 minus H5. However, we have to take note that H1 and H8 is just equal to H6, like this one here, as stated above. So this becomes 0, and M2 becomes H6 minus H5 all over H2 minus H5. Okay? Okay. Those, we may find your H7. Now, after finding the H7, we will now want to find the work of the turbine. Okay, so the work of the turbine here, where do I place that? So work of the turbine is work turbine 1, 2 is equals to H1 minus H2. But the work of the turbine 2, 3 is equal to 1 minus M2 H2 minus H3. Okay? The work of the pump 1 is just equal to 1 minus M2 times work of the pump that has been calculated out of this one. Okay, you just plug in. And work of the pump 2 is equals to M2 because only the mass 2 has been entering in the pump 2. So M2 and the calculated work of the pump 2, which was derived from this one. Okay. So work net is equals to work turbine total minus work pump total. We all add up the pump work and the turbine work. Therefore, your thermal efficiency, the thermal efficiency of the cycle is, say, thermal efficiency is equal to work net over QA. So that ends the discussion for the closed feed water heater. And thank you for your patience listening.